Hey, what's up YouTube? To kickstart 2024, I thought I'd do a video on one of my favorite tech subjects of all times, foliage that nicely reacts to dynamic wind. Now, building a wind system is usually a two-part thing, well, a three-part thing almost. First step is to actually generate and quote-unquote simulate wind. Second step is to make use of that wind and to deform and animate foliage with it, and that's two very different things. People often get confused with Pivot Painter and similar scripts that only gives you the means to apply wind, so it only solves half the problem at most. It doesn't provide you with a unified wind system of some sort, that's what I'm trying to say, right? Also, UE's Pivot Painter material function comes with its own way to generate wind, but again that lives in its own bubble and isn't tied to a global wind system. Speaking of Pivot Painter, there's sometimes a third step involved in building a complex wind system. It's to create a way to reconstruct pivots and possibly even some kind of hierarchy in engine once the foliage asset has been baked into a single static mesh. And that's what you may call skinning, and that's exactly what Pivot Painter does, right? Skinning allows you to apply wind to vertices in a often very intricate and necessary way, again likely using pivots and parents to apply a bunch of rotations in a hierarchical manner and whatnot. So it's three very different things in my opinion. There's what I may call wind generation, wind application, and wind application most often require some kind of vertex skinning. Now, there are simple techniques to apply wind that almost doesn't require any kind of skinning at all. It's not like Pivot Painter as a requirement, far from it. It of course also depends on what kind of foliage you're working with. Applying wind to grass is likely going to be an easier process than applying wind to a complex tree. In today's video, I'm going to focus on the first step, wind generation, and show you an experimental technique to create a 2D wind system using Niagara. A system to generate wind that can be updated in-game to change direction, speed, gust magnitude, turbulence and so on. Pretty cool, and it's going to be a bit of a journey, so make sure to stick until the end. Now, I said it's an experimental technique because it's not really a technique I have seen before, so it still has to be battle tested, I suppose. Plus it has to be put to the test against other existing solutions. As usual, use your best judgment. There are always many ways to do things, and other techniques might better suit your needs. In the second video, I'll show how I built this complex grass shader of mine, and how I applied the generated wind in quite an intricate way to generate complex motion. That, amongst other things, that second video will be packed with plenty of awesome shader tricks. Anyway, in the third and last video, I'll explain my process when it comes to creating pseudo-realistic foliage assets using Blender, my modeling process, skinning process, import and export settings and all that. So consider subscribing if you don't want to miss out on those upcoming videos. Alright, let's get started. First things first, some context. Recently, with GPUs becoming increasingly powerful, we've seen more and more games implementing complex wind systems. It's totally doable nowadays to run a 2D or even a 3D fluid simulation to properly simulate airflow and create a complex and believable wind system. That being said, that type of solution always has the same constraint, it's limited spatially. Meaning, to be performant enough, airflow is usually simulated in a limited amount of space, say around your character or camera, and that's it. So, to simulate and apply wind at medium and far distances, there's usually a fallback solution in place, a much simpler one. And that's the topic of today's video. I'm not going to talk about a complex fluid-driven system. It's something I really want to tackle one day though, but not today. Now, that fallback solution I mentioned is supposedly simpler than a fluid-driven simulation of some kind, but it still comes with many challenges. First, if it needs to blend with a much more complex system up close, well then that fallback system must behave similarly enough that the transition between these two systems, at some arbitrary distance, looks coherent. And it's easier said than done. Second, coming up with a system that performs great, that offers a wide range of controls, that looks believable and that works well over huge distances is hard. Who knew? Although usually such fallback system is kinda low resolution because it's meant to work across large distances. So it most often doesn't have the capacity to handle custom player interaction, custom local wind sources and whatnot. It's just not what that kind of features such system is meant to provide, often because of very good technical reasons, and the system I'm going to show today is no different. So let's take a step back for just a minute. Yeah, I know I'm rambling, but I want to make sure we are all on the same page. One of the cheapest ways to animate grass or any kind of foliage really with wind is to use simple math. For instance, UE has a built-in node that does just that. It looks complicated at first because it's a huge mess. That's a bit sad, so let's first just reorganize that material function. Voila, that's the same exact function but cleaned. Now that we can make sense of it, let's pick it apart real quick. That's the XYZ world coordinates scaled in two different ways to create two signals. Those coordinates are offset based on the game time in XYZ for that signal and in the Y direction only for that one. Then that just makes this position loop on and creates a bilinear gradient. Let's visualize this real quick. First signal, second signal, okay. Then that bit here may look strange, but if you're familiar with smoothing functions, you can easily guess what this is. Speaking of smoothing functions, this website is great. I'll put a link to it in the video description below. Now, back in the days, I had no clue what this was. So today I'd say to my younger self, well, look at what kind of value this is working with. I know this is guaranteed to be in a 0 to 1 range. So let's just plot this function with a value between 0 and 1 and see what it outputs. And UE has this very handy function to do just that. So let's copy that bit and let's use the texture coordinates horizontal axis as our x. This is x, right? It's linear as expected. And this is x once that function is applied. And it is indeed just a smoothing function. This gives something similar to a remapped sine or cosine function, but without using a slow trigonometry function. Now, we are still working with an XYZ value at this point though, so to get an angle, those two signals are converted into a single scalar value in two different ways, a vector length and a dot product. Same but different. That gives two values oscillating at different frequencies and they are added together to be used as a rotation angle, and the rotation is done around a fixed arbitrary axis and an arbitrary pivot point to offset vertices and create that bobbing motion. It's quite boring, there are simpler and way better looking alternatives to this, but that's a topic on its own. You can of course exist to create something more intricate, but generally this method has its limits. It's hard to create wind that feels alive with this method, wind that actually looks like positive and negative pressure waves moving across the landscape with varying direction, speed and intensity, right? So usually to do this, the trick is to use some kind of tiling noise texture, projected and scrolled in world space. Then use the texture value to either modulate sine waves or apply an offset encoded directly in that texture, same but different, it doesn't matter. With this technique, well, it's quite easy to create nice wind patterns, something that looks like actual airflow moving across the landscape, right? However, this technique has a huge limitation. Wind speed and direction cannot be changed. Not easily at least. And that's baffling to quite a lot of junior tech artists. Why is that? Well, when you think about it, scrolling a texture is just a matter of offsetting texture coordinates in a certain direction by a certain distance. And usually that distance is the game time and some multiplier. Say I've been playing my games for 10 minutes, that's 600 seconds. So with a scroll speed of say 1, UVs would be offset by 600 units in some direction, right? And so changing that scroll speed doesn't result in the next texture coordinates to be offset by a bit more. No, it results in new texture coordinates, offset still in the same direction, but by an entire new distance. Let's increase the scroll speed by say 0.1. 600 seconds times 1.1, that's 660 units. So tweaking the scroll value even ever so slightly from 1 to 1.1, having played the game for around 10 minutes, results in a big jump in texture coordinates, 60 units. Thus, that results in a huge burst of texture movement, if that makes sense, and why it behaves a bit strangely. Same principle with the scroll direction. That just results in a huge burst of texture movement for the same exact reason. Texture coordinates are now offset in a new direction from the origin of time, so a very, very drastic change, even if the direction ever so slightly changed. Not only that, but you also likely need to rotate the wind texture, so whatever wave pattern you have in that texture faces the wind direction, right? And rotation comes with the same exact issue. It's done around a pivot point, so the further away from that pivot point, the bigger the change in position. Essentially, changing the wind speed or direction breaks the spatial coherence, if I may say, and results in noise. Now, there are solutions to this issue. My favorite tech talk of all time, this God of War tech talk, actually explains a possible solution, but it's complex to say the least. I've yet to fully understand it, to be honest, something has yet to click in my brain. There are also other shenanigans you can employ to somewhat fix this, but I've yet to find a simple and elegant solution that doesn't rely on multiple texture samples or all kinds of other nasty tricks. However, that made me think of something. A long time ago I built this weather system. I should revisit it someday and release it. Anyway, it featured all kind of cool tricks, including a dynamic wind solution. The technique was simple. I spawned a bunch of sprites that moved according to the wind direction and speed, and I captured these sprites using a top-down scene capture component. The resulting texture didn't tile, and at the time I didn't care. It was projected as is across the entire level because that level was quite small. But that meant that solution wouldn't work for, say, a large open world, right? I'd either need a huge texture or I need this texture to tile, so I could repeat it a bunch of times all the way to the horizon or something. And so recently I thought to myself, well, this idea isn't that bad. Sure, it relies on a scene capture component and I hate that. A scene capture component definitely comes at a cost, but hey, for now, let's pay that cost and see if a proof of concept at least works. You may afford it anyway. Again, it depends on your project, budget and all, right? Spoiler alert, it turns out relying on a scene capture component did indeed come at a huge cost, and I had a gut feeling a better solution was out there. And I kept digging and I eventually found a solution. So keep watching because I'm first going to stick with my original method that makes use of a scene capture component, okay? It will be easier for me to explain the key principle behind my system. Then I'll show you how I managed to get rid of that annoying scene capture component and improve performance by 20 times. For now though, let's keep things simple and use a scene capture component, and let's first try to solve this tiling issue. Now, there are post-process solutions to make any texture tile, like I explained in a previous video. You can sample a texture a bunch of times and fade out the edges, but that method comes with a few downsides, and some patterns don't tile very well and result in a lot of blur with that technique. Plus it's a post-process effect, right? So I would need to capture the wind texture first, as is, then sample it a bunch of times and render it into another render target to make it tile, and I didn't want to do that. I thought the scene capture component was already expensive enough, so I wanted to see if I could find another solution. Well, let's take a step back and think about what makes a texture tile. Yeah, I know I'm delaying the actual tutorial a bit, but I like to explain my thought process. Feel free to use the timestamps to skip the boring part. Let's say I want to create tiling bricks. I could start by laying bricks within that region. Then I would duplicate meshes crossing the left edge and move them over by one entire tile width to the right. And same with meshes crossing the top edge. Then I'd probably have to move bricks within the center region to fix overlaps and whatnot, but that's it. This pattern tiles because whatever crosses this left edge is duplicated to reappear on that other side, if that makes sense. Same with the top edge. And this could serve as a base mesh in the brush, and with its warp mode turned on each brush, I could sculpt a tiling brick material quite easily. So when you think about it, at most a brick has to be duplicated up to 3 times when in a corner. Most often just 2 times when crossing a single edge. So, well, following that principle, what if a brick was a Niagara particle? What if a single particle in a Niagara particle system was made to render 4 sprites, spread out like this? This would tile, right? Yes, but not always. See, if that particle would move over here, it would no longer tile. So I would actually need to render 9 sprites to cover all edge cases. Not great. Well, it turns out 4 times is enough. Just have to offset them all by half a tile and have the particle's position be at the center. Now, regardless of where this particle is within that region, this setup results in a quote-unquote tiling particle. Then scale and rotation could be applied to these sprites individually and it would still tile, right? As long as sprites don't exceed the tile width when rotated and scaled though. And turns out, this idea is very easy to apply in Niagara. The only remaining issue is to make sure this particle stays within that region when moved according to the wind. And that's also super easy to do. When this particle crosses an edge, just move it by an entire tile in the opposite direction, and that's it. Then spawn a bunch of them to create a couple of wind gusts, capture the result with a scene capture component, and voila! That's a tiling dynamically generated wind texture that can nicely react to changes in wind speed and direction. And that's the idea behind my wind system. To sum up, It's first and foremost designed to model large-scale wind gusts using what I may call wave particles. Wave particles are iterated on and thus can change direction and speed based on the wind direction and speed, something you can't easily do when scrolling a texture. Those wave particles tile so that the generated wind texture can be tiled and spread across large distances. Because of that tiling though, the system is not designed to handle custom interactions, because any interaction would obviously be repeated in the distance with the tiling, right? That's usually solved with another system, one layered on top of that global wind system, one that is locally bound and typically somewhat centered around your camera or player at all times. Voila, that's the theory. Now let's dive deeper and see how a first implementation is possible using a scene capture component, shall we? First I have a simple blueprint actor. Its tick event is disabled. It owns a scene capture component and a Niagara component. That scene capture component is configured in the construction script. It captures the scene color in HDR and renders the Niagara system using its show only list. And that Niagara system is visible to scene captures only. Then that scene capture component's transform is set to render particles from a top-down orthographic view, right? And the orthographic width is also set and sent to that Niagara system. Finally, the scene capture component is set to capture every frame and is made to render nothing but translucent particles. Its render target is also set, of course. It's as small as possible to be as efficient as possible. 128 is plenty enough, I think. It's supposed to contain 2-dimensional wind data, so 2 channels are enough. 32 bits is overkill though, and 8 bits would be annoying to use, because wind speed would need to be normalized to be remapped in a 0 to 1 range, and since the accumulated speed is kinda arbitrary and hard to know precisely, let's go with 16 bits. I also use a second render target, same settings. That one is used to store the wind previously rendered, very important, but more on that in a minute. Finally, that blueprint has a few functions. Basically, for each user exposed wind parameter, it has a set and get method, nothing too complicated. Say set wind force, that just updates a vector in a material parameter collection to store the wind direction and force. That way it can be accessed in any material if needed. But more importantly, a Niagara parameter collection is linked to this material parameter collection. That way any Niagara system can also very easily access the wind direction and speed. Now I could have that blueprint actor dialog with that Niagara component directly to send the wind direction and speed, like here with the orthographic width, but using a Niagara parameter collection instead can be useful in case you want to make, say, a particle system to create rain or a weather effect of some kind, and have that effect react to the wind as well. So from a user perspective, you just need to drag that blueprint in your scene. Then get a reference to that blueprint actor with your preferred method and access its public functions to tweak the wind parameters. And then use those 2 render targets in your foliage materials to apply the 2D wind in your own way, more on that later on. Cool, that's the boilerplate code if I may say. Most of the magic happens in that Niagara system, so let's check it out. First things first, this is a GPU emitter and it works in local space. I set its bounds mode to fixed, and to reduce this emitter's cost I turned off interpolated spawning. This comes with a few caveats, but I'll just need to be cautious with the particle's initialization logic and it should be fine. Next I have a spawn rate module set to 20, so quite low. Next is the initialize particle module, nothing fancy going on here. Lifetime is set to 3 seconds, why not? Here I just make sure opacity is set to 0 at first. I want particles to fade in, so opacity must be right away correctly set because of that interpolated spawning setting turned off. Size is first set to be the tile width in X and half of it in Y. It's then uniformly and randomly scaled down. Then I spawn particles in a box based on the tile width. Then I make sure particles are all facing the z-axis. Next I have a custom module to implement the tiling logic, so it needs to know the tile width. Here first I get the particle's position, the position is irrelevant and set to 0. And to make a particle stay within the tiling region, it's simply offset by how many tiles it's quote-unquote exceeding in the opposite direction, if that makes sense. Next, based on this tiled particle's position, I generate 4 positions. Each is offset by half a tile to create the tiling pattern I explained earlier. And let's see right away what these vectors are used for. See, down there I have 4 sprite renderers. I suspect this is not ideal and comes with some overhead, but oh well. In each renderer, I override the position binding, so this sprite isn't rendered at the particle's position anymore, but at one of these 4 offset positions. Sprites are then oriented based on their velocity and they render a simple radial gradient colored based on that 2D velocity. And that's most of it really. The rest is quite simple. On particle update, I compute a new velocity based on the current wind direction and speed, accessed from the Niagara parameter collection I mentioned earlier. Both the wind direction and speed are somewhat randomized per particle, and I then lerp towards that new velocity to create some kind of inertia, right? Finally, that velocity is applied to move particles. One last crucial step, the updated position is made to tile. That's the same module I used here, right? Oh, and one more thing, just have to set the particle's color based on its 2D velocity, and a simple curve is sampled using the particle's normalized edge to fade that particle in and out. And that's it. That creates a tiling, dynamically generated wind texture. Neat. Let's see how it can be applied to cheaply animate grass. I won't spend too much time on that bit today because this will be the subject of the next video. I'll dive deep into all kinds of crazy techniques, so for now I'll keep things simple. So this wind texture is the accumulation of particles' velocity in x and y, masked with some simple radial gradients, right? That super duper simple method already creates nice wind gusts on its own and can be projected in world space to offset vertices in x and y. So let's first mask this offset along the grass length. And this can be done in many ways. I usually encode the grass normalized length in UVs, but you could bake a gradient in a texture, use vertex color, or use any other technique. You could also use the mesh's local vertex position in Z, but that's going to give you a non-normalized value in centimeters, so wind should probably be scaled accordingly. You could normalize that position using the local bounds in Z though. Keep in mind that with this method, if you for instance want to pin the roots, those vertices need to be at 0 in Z. Anyway, it still doesn't look great though. This obviously doesn't look like a rotation, right? Well, I could safely normalize this wind offset to get the wind direction and derive a rotation axis, and then get the wind force, so the length, to compute a rotation angle. But that method requires pivots to be baked and uses trigonometry. And I might not have the memory budget or even the tools to bake pivots, nor the budget to compute a true rotation. It's not that costly, but who knows, maybe I'm on a very tight budget. So there's a cheap trick I already explained in my stylized grass video to fake a rotation, a trick that doesn't even require pivots to be baked. It's a technique I learned watching that God of War tech talk, told you it was my favorite one. Let's use this material function to apply a spherical reprojection. That's going to deform the mesh a bit with large offsets, something I already explained as well, but that's most often not that noticeable. And voila, super easy, right? Now let's use world space normals and use the reprojection axis for the normal. Then maybe use the two-sided foliage shader, add the necessary parameters, and voila, you get something that looks somewhat decent already, and it reacts nicely to the wind. However, it may not be too visible on YouTube due to the video compression, but you might see that the more wind, the more blurry and noisy the grass looks. Those visual artifacts are due to all the temporal effects going on in UE, TAA, TSR and such. Those algorithms use a velocity buffer to help get rid of most of the ghosting, and to output a velocity, a material needs to compute a position delta. That's done using the previous frame switch node. Feel free to watch my waterfall video for more information on that node. So I need to tell the shader, hey, this frame applies that much wind, but also tell it, hey, that much wind was applied last frame. That's going to allow the material to output a velocity, but obviously I can't just use this render target a second time. This contains the wind to apply this frame, not the wind that was applied last frame, right? So before this render target is updated, I just need to copy it into another render target. And there are many solutions to do this. One simple solution is to use a draw material to render target node on tick to simply copy that render target into a second render target before the scene capture component overrides it with the latest capture. Always pay attention to the material settings when drawing onto render target though. You might want to enable this option to output negative emissive values, for instance. Okay, so when copied, at that time, that render target still contains the wind data that was captured the frame before, precisely what I need, and then it's overridden with the capture and thus the data for this frame. Hopefully that makes sense. However, this is only called in-game, and that creates quite a bad user experience. because then in editor it results in that kind of crap. That's due to the material outputting a wrong velocity, since that render target is only updated when in-game. So I'd like a solution that both works in editor and in-game. Niagara to the rescue then. I use the second emitter. Here I initialize a grid to the interface and set its number of cells to match that render target size in X and Y. Then in a first simulation stage, I read the render target pixel value at each grid cell and store that value in it. Next, in a second simulation stage, for each grid cell, I get the 2D wind value it contains and write it into the corresponding render target pixel. That's it. However, because a scene capture component renders things at the very beginning of the frame, the value I copy from that render target to that other one is already the updated value, not the previous one. It's an exact duplicate essentially, and it's definitely not what I want. Ideally, I'd like this to be called before the scene capture component does its capture, but there's no easy way to do this as far as I know. So let's tweak this emitter's logic. Before overriding that wind value with the up-to-date wind value I'm reading from that render target, I'm going to store it into another vector 2D. That essentially creates a one-frame delay, and that's the value I write to that render target down there, so it now contains the wind that was captured last frame. Neat. And voila, feed that second render target to the shader, and right away it gets rid of most of the ghosting and applies the motion blur. Awesome. I can then push the idea further. For instance, I could use another emitter to render a single quad. Quad used to render a material to maybe output a constant value to create a constant wind push, right? And possibly some animated noise to add variable high frequency turbulence and so on and so on. Speaking of noise, a little side note. Now that I'm using a Niagara emitter, I can somewhat fix some of the issues I mentioned earlier with the texture scroll speed and direction, leading to bursts of texture movement when changed. Meaning I can create a vector 2D named, say, texture coordinate offset and update it according to the wind direction and speed. That offset is periodically ticked and isn't based on the game time, right? So changing, say, the scroll speed doesn't result in a big sudden change. It just makes the next update be slightly larger, if that makes sense. So I can use that offset to sample a noise texture on that quad and watch it properly react to changes in wind direction and speed. But again, this texture would ideally need to be rotated to face the wind direction, so there's still that issue to solve, and it's complicated. Anyway, I kinda like this wind technique for its high versatility. I feel like I can do a lot with it. The one downside is its performance. The scene capture component is a huge bottleneck, even more so in UE5 for some reason. The Niagara system itself is super duper cheap, almost negligible in cost, but the scene capture component cost is all over the place and can be huge at times. It's super frustrating, I hate scene capture components. This costing 1 millisecond to render makes no sense to me. There's a huge bottleneck somewhere, whatever. Now, when I wrote a first draft for this video script, I intended to stop here and say, it's costly, but the system is just a proof of concept anyway, so whatever, blah blah blah, thanks for watching, see ya. But I had the gut feeling that I could find a solution that doesn't require a scene capture component, and indeed I did find one. And I'm sure my solution could be even further improved by tenfolds, but for now this is as good as it's gonna get. Now it's a bit advanced and I don't feel like doing a step-by-step tutorial on the most advanced Niagara features right now, so I'll be somewhat brief, I apologize, buckle up. Alright, let's take a step back. What do I need this scene capture component for? Well, I need to render particles. Each particle renders its 2D velocity and uses a super duper simple spherical mask for its opacity, as well as a fade in and out based on its normalized age. So in a way, and this was the thinking that sparked the idea of a custom renderer in my mind, I can tell right away that I don't need this material and those sprite renderers. Just by accessing the particle's position, age and velocity, I could compute a spherical gradient and output the same exact pixels. And that's exactly what I'm going to do. I'm going to create my own particle system and rasterize particles myself using an array and a grid 2D interface. Sounds complicated, and if you're not familiar with Niagara and HLSL, it probably is, but the idea is pretty straightforward. Again, I'll be somewhat brief here. Basically, for each particle, I need a way to store and iterate on a 2D position, 2D velocity, although here I'm going to choose to split that into a 2D direction and speed, radius, normalized age, lifetime, opacity, possibly, although it could be derived from the normalized age, and a couple of extra parameters to tell a particle how to react to the wind. So if I know my math, that's 12 floats. Neat. So in Niagara, I created a vector-4 array to create 3 vec4s per particle. And that for a fixed amount of particles. 60 is plenty enough. Then in a third simulation stage, I loop through each particle. I then have some HLSL code. I get the particle's parameters, I check if the particle's age is 0, and thus if it has to be spawned. I increment its normalized age, and if it equals or exceeds 1, then it means the particle died and is immediately recycled. Then I compute that particle's movement direction, obviously based on the wind direction, and the wind direction can be somewhat randomized per particle. Next I spawn or recycle that particle if it should be, meaning I initialize all its parameters. Else I just lerp its current movement direction and speed towards the latest randomized wind direction and speed. Next I derive a bilinear gradient from its normalized age to compute its opacity. Here I apply its movement, and then I make sure this particle stays within the quote-unquote render region, same principle as before with the scene capture component, right? Finally, I update those parameters, and voila. There's yet no way to visualize this, but I've now a bunch of particles moving within a 500 by 500 cm area and reacting to the wind and all. Now it's just a matter of rendering those particles. Here I chose to go with a brute force approach, and I reckon there's a smarter way to do this, but it's as good as it's gonna get for now. I used a grid2D interface, sized to match the wind render target's width and height. Then in a third simulation stage, I loop through each grid cell. I then loop through all particles and get each particle's parameters. Here I do a bunch of safety checks. I compute that particle's forward and right axis based on its movement direction. I then do a for loop to offset that particle's position 4 times and make it tile, right? Same principle as before. And then I check how distant that offset position is to the grid cell to derive 2 gradients. One along the particle's forward axis and one along the particle's right axis, and both are based on the particle's radius. That creates some kind of box mask around the particle's position. And then I accumulate wind in that 2D cell based on the particle's velocity, mass and opacity, and voila! I also add a constant push and turbulence into the mix, and then it's just a matter of exporting this 2D grid, and that's done using another simulation stage. And voila! With 60 particles the cost is around 0.05 milliseconds on a 4070. And again I reckon there are ways to optimize this, but still, compared to 1 millisecond when using a scene capture component, it's already insanely cheaper. And now that I don't rely on a scene capture component anymore, I can use an RGBA render target and now super easily pack the previous wind value in its blue and alpha channels, and thus use a single texture sampler to sample both the current and previous wind in my grass material. And that's how I built my 2D wind system without relying on any scene capture component. Neat. I then did a couple of tweaks to my wind manager actor, nothing drastic, but I still want to mention it. See, it still has quite a few controls over the individual wind components, right? Direction, speed, turbulence, gust and so on. But to simplify everything, I made a struct to list all available controls. I then made an array to create a list of wind presets. So I could for instance create 12 presets to recreate the Beaufort scale. Then tweaking the wind is just a matter of calling that one single function to set the direction, obviously, and drive an overall intensity parameter in a 0 to 1 range. That's used to quote-unquote select a preset. Intensity is 0, that's the first preset, 1, the last one. And in between 0 and 1, presets are then linearly interpolated to create a smooth ramp-up in intensity. Cool. That's it, files are available as a tier 2 reward on my Patreon, but please note that it doesn't include the grass assets and the complex grass material. That tier 2 project is just the wind system along with a simple grass example. The more advanced realistic grass will be available soon at a tier 3 level. I also have many other great educational projects, systems and assets on my Patreon, so feel free to check it out. Any support is much appreciated. Speaking of support, feel free to leave a like if you liked the video and consider subscribing. Thanks so much to all my Patreon supporters, I simply wouldn't be able to do this without you guys, so big thumbs up to you all. Alright, that's it, I'll see you in the next video. I'll dive deep into my complex realistic grass shader, so stay tuned. In the meantime, take care of yourself. Bye bye!